All right. Not sure what's going on there at the beginning. This is going to be a video over page 7 of your notes, finding the pH of a salt solution. So you should have done a little bit already with trying to determine if a compound is acidic or basic, if it is a salt. So this is telling you find the pH of a 0.3 molar NaF solution. 0.3 molar NaF solution. So first thing we have to figure out is that an acid, a base, or if it's neutral, we know the pH is 7. So if you remember your rules here, sodium ions do not affect pH. Sodium ions do not affect pH. They don't have the ability to gain a hydrogen or lose a hydrogen, so those don't affect pH. Fluorine ions do affect pH. They have the ability to gain a hydrogen. So let's write our equilibrium. So put it plus HOH. Okay, this is a weak base. So our pH is going to be above 7 when we're done here. Has the ability to take a hydrogen and make HF, which remember would be the conjugate acid of this weak base, plus OH negatives. That's why it's a base. It's making OH negatives in water. Sorry, I'm seeing if my video is working. It doesn't seem to be quite right. Notice this gives you the Ka of HF. Okay, gives you the Ka of that. Well, we really don't need the Ka of that. We really need the Kb of F negative. Okay, really need the Kb of that since we are working with a base. So let's figure that out right now. So remember, Ka times Kb always equals 1 times 10 to the negative 14th. So we need to take 1 times 10 to the negative 14th divided by this Ka value, 7.2 times 10 to the negative 4th, and that will give us the Kb of F negative. And that Kb value is, I'm on the wrong page, that Kb value is 1.4 times 10 to the negative 11th. So the Kb of F negative is 1.4 times 10 to the negative 11th. All right. We know initially this is a 0.3 molar solution. Don't need to worry about water as part of this. These are both 0 molar to start with. So if we say, okay, this is going down by x, so at equilibrium it's going to be 0.3 minus x. These are both going up by x. So at equilibrium, they're both going to be x. So now if we write our K expression, products over reactants, we can go our Kb of F negative equals x times x, so x squared, over the initial concentration of this, 0.3 minus x. Remember, we can ignore that x in the denominator because it's going to be such a small amount, and just make this 0.3. Our Kb value out here is 1.4 times 10 to the negative 11th. Remember, if we are using a Kb value, we are finding concentration of OH negative. So our x value is going to be concentration of OH negative, so we can find POH and pH from there. Cross multiply square root. X, remember, is the concentration of OH negative. It is also the concentration of this weak acid. We don't need to know that. We want to know the concentration of OH negative in this solution, which is 2 times 10 to the negative 6th molar. Take the negative log of that would give you the POH, negative log of this number. So the POH is 5.69, and the pH would be 14 minus that number, which is 8.31. So first thing is figuring out if this was an acid or a base. Once I figured out it was a base, write your expression. It gave me the Ka of its conjugate, so I had to find the Kb from that. Kb equals x squared over the initial concentration, knowing that x is my concentration of OH negative. And a little bit above 7 is a weak base. All right, we'll do one more of those. Find the pH of 0.3 molar NH4Cl if the Kb of NH3 is 1.8 times 10 to the negative 5th. So again, we've got to figure out, is this solution an acid, a base, or neutral? Well, NH4 ions are weak acids. They have the ability to give a hydrogen and act as an acid. Cl negative ions do not affect pH. So those do not affect it. So we're going to go NH4 plus dissociating into H plus NH3. Again, weak acid, conjugate base. Notice it gives us the Kb of this. We really need the Ka of NH4 plus. So we'll have to do the same thing we did last time. Ka times Kb equals 1 times 10 to the 14th. So I'm not going to show that unless you guys need me to. The Ka would equal, remember, you're going to take 1 times 10 to the 14th divided by that number. The Ka of this is 5.6 times 10 to the negative 10. 5.6 times 10 to the negative 10th. Again, that is the Ka of NH4 plus. Initial concentration here is 0.300, going down by x. So at equilibrium, this is going to be 0.3 minus x. Both of these are going to be x. So same thing as last time, we can say the Ka equals x squared, these two things, over 0.3 minus x. But we can ignore that x in the denominator. It's going to be very small. Put our Ka value out here, 5.6 times 10 to the negative 10th. Cross multiply that times 0.3, take the square root. X, remember, always figure out what x is. If you're using a Ka value, x is always the concentration H plus. If it's a Kb value, it's concentration H negative. So find our x here is 1.3 times 10 to the negative 5th molar. Negative log of that should give us a pH close to 5, probably a little bit lower than that because we're above 1. And negative log of that gives us a pH of 4.89. So now we can start doing things with salts because they do typically affect the pH in some way, shape, or form. Have a good day.